Financial instruments are in essence the promise of future payments from a borrower to a lender. Because the timing of such payments can vary from contract to contract, we need to be able to compare different timing structures analytically. While interest rates do fulfill this function eventually, their calculation requires one additional step, and that is the concept of present values, or so-called present discounted values. You may be familiar with this discussion if you've ever heard about the time value of money. When we're thinking about the future, we generally value things we can have sooner more than things we have to wait for a longer period of time. This is a behavior known as discounting. Discounting is a behavioral component in biology and in economics, but it makes obvious sense in financial contracts. For instance, if I offered you $100 today, they will be worth more to you than the same $100 will be 15 years from now, even if we're ignoring inflation. The reason for this is that if you have these funds today and invest them, say, at a 1% annual interest rate, the value of these $100 15 years from now wouldn't be just $100, it would be approximately $116, which is of course more than $100. In other words, there is an opportunity cost to wait if you could invest money in the meantime. To develop a sense of how discounting works mathematically, we'll start by doing the opposite. That is, we find so-called future values, which indicate what some amount of money today invested at a given interest rate will be worth some number of years in the future. This comes more intuitively to most people that have never seen a present value before, since it is a type of calculation we have all made at some point and should therefore understand more easily. For this illustration, we will focus on discount bonds and simple loans. For simplicity, largely, but all the principles extend to more complicated instruments without any loss of generality. Let's work through a simple example of a simple loan to find future values. Say lender L lends to borrower B an initial amount of $2,500, apologies about that, on the 1st of September 2020. What is the amount of money that B will owe to L? In other words, what is the future value of these loans? Say 1 year from now, if the interest rate is 4%, or what it would be worth if you loan $2,500 at 4% interest for 5 years. Now, the first case should be pretty straightforward. If you borrow $2,500 today at an interest rate of 4%, you have to pay back the $2,500, and you have to pay back 4% of $2,500, what happens to be $100. So the overall amount you pay is $2,500 times 1 plus 0.04, the interest rate, which is equal to $2,600. Easy question. What about case B, the maturity case of 5 years? To get there, let's answer this question stepwise. For instance, what is the value of these $2,500 at 4% 2 years from now? Well, at the end of the first year, they were worth $2,600. Now, if I'm reinvesting them for another year at 4% interest, you'll get the original $2,600 plus 4% of that, which is about $104. So after 2 years, your original $2,500 are equal to $2,704. Now notice, of course, that a borrower has to pay interest not just in the original principal, but also on interest accrued over time. This is something that we refer to as compounding of interest rates. Now, by substitution, I can express the end of the 2-year future value of $2,500 as a function of the original $2,500. It's simply $2,500 times 1 plus the interest rate of 0.04 squared. And that I can generalize out to any number of n years. The future value of $2,500 invested at 4% n years from now is equal to 2,500 times 1 plus 0.04, this should be a point, not a comma, to the power of n. So for 5 years, for instance, $2,500 times 1 plus 0.04 to the power of 5 is roughly $3,040. So that's what you would owe after 5 years from today. Now, values determined in this manner are so-called future values, and those should be concepts you're fairly familiar with. They simply indicate the value of some amount X you invest today at an interest rate I n years from now. Reversing this process, finding the equivalent of some future amount X in years from now, invested at some interest rate, is referred to as discounting. And resulting values then are referred to as present values or present discounted values. They simply indicate the value of some future cost of benefit as of today. Let's go through an example. Say, for instance, someone offers you $2,900 4 years from today. What is the present value of these $2,900 as of today if the interest rate is 4%? This is equivalent to asking, what is the amount of money I need to have today? If I invest that at 4%, that will equal exactly $2,900 4 years from now. The math here is identical to earlier. The only difference is that in this case we know the future value, but we don't know the initial present value, PV. We know that whatever we have to invest today, paying off interest 4 times, 4% interest, will yield $2,900 in the future. So to figure out what the present value of these $2,900 are, we simply have to solve this equation for PV. Now, dividing both sides by 1 plus 0.04 to the power of 4 yields a present value of $2,478.93. If you invest this amount for 4 years at an interest rate of 4%, it will yield exactly $2,900 from now. That's what a present value is. Now, in general, the present value of any single payment, and therefore the present value of a simple loan or a discount bond, is given by the future payment divided by 1 plus I to the power of n, where n is the number of times the asset pays interest. What do we do with more complicated assets? In principle, there really is no difference here. I know this looks very complicated, but in order to find the present value of something like a coupon bond or a fully amortized bond, something that has multiple future payments, B0, B1, B2, and Vn, you simply find the present discounted value of each individual payment, V0, V1 1 year from now, V2 2 years from now, Vn n years from now, and add all of that together. That will give you the present value of the entire payment stream. Now, mathematically, it's inconvenient to write it in these long, clunky conventions. So as a consequence, we use these summation operators. I know they terrify people, so I'm not going to use you to ask them, but I will strongly encourage it because it's a lot shorter. What this is simply saying is the present value of whatever this payment stream is, it could be a coupon bond, are the payments in period t discounted back t times, and then we just add all of these payments together. So this expression here is synonymous to this much longer expression over here.